All right, I guess I'll go ahead and get started. So yeah, this is going to be a series on how to write games in C using a library called SDL. Uh, yeah, so the idea is to write a simple playable game in about 1 or 2 hours per session, and we'll be starting with very simple games like Pong or Breakout, and working our way up to more complex titles like top-down shooters, side-scrollers, eventually 3D games using OpenGL. And yeah, so as a prerequisite, you should know the basics of C or a C-like language like C++, or this might be a little tough to follow along with. So yeah, basic knowledge of things like variables, if statements, functions, loops, pointers, structures, that should be enough to get you by. If you need to brush up on C beforehand, there are a bunch of tutorials scattered all around the internet, and you can come back to the recording of this, I guess, when you're all caught up. So in addition to basic knowledge of C, it'll also be helpful to know how to link third-party libraries into your program using the IDE or build environment of your choice. And today I'm going to be using Xcode. I might mix that up a bit because a lot of game dev happens on Windows, so learning how to set all this stuff up on Windows is pretty valuable as well. So yeah, let's dive into it. So why are we using C instead of a higher level language like C++ or C Sharp or even an engine like Unity or Unreal? So those high level languages are fine, and engines are perfectly fine too. But the choice for using C for this tutorial is there are two components to it. So one, there's a tendency among developers to over-rely on complicated abstractions for simple tasks. And while it's a good instinct to reach for high-level abstractions to maximize productivity, we frequently underestimate how powerful simple solutions can be. So yeah, by using a language that's lacking in a lot of modern bells and whistles, we're sort of incentivized to kind of focus strictly on the problem at hand rather than sort of getting lost in the weeds, building this big complex system. Uh, yeah, so our objective here is to learn how powerful we can be despite not having the most advanced, sophisticated tools. So, part one. Part two is even if we don't end up writing or shipping games in pure C, by building things at a lower level, we gain insights into how some of the higher level tools work when we do use them. At the end of the day, a lot of these high level frameworks and tools and engines are kind of leaky abstractions. So if you're unfamiliar with what a leaky abstraction is, the basic idea is that it's when you use something that's higher level, but some sort of knowledge of its internal structure or operation is useful for making the most effective use of it. So as an example, in the game programming world, you might run into an issue where like you're using an engine and you're drawing like say 100 of the same character on the screen at the same time, and it runs pretty fast because the engine is smart enough to say like, okay, I'm drawing this thing, but I'm drawing 100 of the same thing, so I'm going to batch all these things together, and I'm going to use all this magic under the hood to make sure that I'm not, like repeating a bunch of work. And, let's say you like do some minor customization to one of those objects, and then all of a sudden your frame rate tanks. So if you're not familiar with the sort of lower level of how renderers work, how, batching and draw calls and all that, all that stuff works, then you might be kind of mystified about why that's going on. But if you have experience, kind of working at that level, that allows you to sort of have some insight into why you might be having a performance dip. And not only that, but say you're using a source available engine like Unreal, and say there's a bug in one of the components, or if there's some functionality that it doesn't have that you want to add to it, well, if you know how to write at a lower level, you're gonna have the skills to go ahead and extend the engine to do what you want it to do. So, in addition to these practical reasons, I also just think it's fun, and hopefully you're gonna think it's fun too. So, yeah, let's go ahead and dive into it. So, to write games in C, we're gonna need a library to get something onto the screen. We need something to get something on the screen. We need something to read our keyboard and mouse input. And for that task, we're going to be using something called SDL. So let me go ahead and pull that up. Yeah, so SDL is it's basically a cross-platform library that lets you access things like the monitor, the keyboard, the mouse, various game controllers. It lets you do sound output. It has some functionality for threads and timers, and it's basically a cross-platform way of accessing system components so that when we write our game, we don't have to write, Windows-specific code or Mac-specific code. SDL just kind of handles the platform-specific stuff for us so that we can focus on writing our game. But it's not an engine or a framework where frameworks implement a bunch of functionality on top of that basic I/O stuff, right? So a framework would be something like XNA or Monogame. Uh, an engine would be something like Coco's 2D or Unreal, where we have this higher level structure that we're sort of plugging things into. So SDL is not in that category. SDL just acts as a layer between our game and our OS to sort of make things a bit generic. Now you might be asking, like, okay, we're doing this tutorial lesson in C, and so why are we using this library to kind of abstract things out? So the purpose of using C isn't to avoid abstraction just for the sake of avoiding abstraction. The idea is to sort of be more thoughtful about the abstractions that we do use. And in the case of using SDL, we have a fairly lightweight library that it kind of cuts down on platform-specific boilerplate code, and that's great for just making this set of lessons as accessible as possible. Yeah, so SDL runs on Windows, on Linux, on Mac, iOS, Android, FreeBSD, even OSs you probably haven't heard of, like Haiku. Don't know what Haiku is? Well, congrats if you use SDL, then your game probably runs on it. So yeah, the way that you install SDL depends on what OS or compiler you're using. So if you're on a Unix environment like Mac or Linux, then you could use your package manager to install it. If you're on Windows, then your best bet is probably downloading it from here. There's what you're gonna want likely is if you're using Visual Studio, you're gonna want this one, SDL2 Dev VC. If you're using something like CodeBlocks, then it's probably got MinGW in the background, so you're gonna want to use this one. And like I said, I'm on Mac OS today, but I might do a feature stream on Windows just to sort of show how to set things up over there. But let me go ahead and so yeah. So as I mentioned, the way that I have it set up here is using Homebrew. So if you do brew install SDL2 is the current version. You might run into SDL1, but bear in mind that it's actually pretty old at this point. Like SDL2's been out for almost a decade now, and yeah, SDL1 and SDL2 are not API compatible with each other. So SDL2 is the one that you want, and I've already got it installed, so of course that didn't work quite right, or it didn't, it gave me an error. It's fine though. So if we install SDL via Homebrew, then our libs and our includes are going to be inside of USR local. So just to show that here. So yeah, the ones that we're going to want are libsdl2.a and libsdl2 main.a, and you see that SDL2, that's actually a folder, and that has all of our header files that we're going to need to access the API. So let's go ahead and get started and create a project. Yeah, so we're going to create a Mac project, and we could do this either as an app or a command line tool. Command line tool is going to be a little bit simpler, but an app might be more what you want if you want to go ahead and distribute your project. But we're just going to stick to command line tool for now. We're going to make sure that our language is C, and then we're going to say, yeah, just give it a name, call it Hello Pong, why not? Go ahead and create that. All right, so now the first thing we want to do is make sure that we're all linked and we're able to compile and run against the SDL version that we just installed. So if we go into build settings, I'll look for, you want to find header search paths and library search paths. And we're going to add the directory so that our homebrew stuff is actually discoverable by your project. Okay, so step one. And our next step under build phases here is we want to link with those libs. We want to link with SDL2 and SDL2 main. So let's go ahead and add those. There we go. Okay, so we have our include set up. We have our library linked into our code here. So let's go ahead and try to use it. Okay, let's try running this and see what happens. And we have a crash. Why do we have a crash? Well, on the latest version of macOS, Catalina, we have some extra security features, and basically the OS does not like it when you link to a binary that you did not sign yourself. And in this case, we grabbed SDL off of Homebrew, and it has a different code signature than what we have going on, so the OS just crashed out. So there are a couple solutions to this. One is to just download SDL and build it yourself. And the other is to just add an entitlement that allows us to kind of keep on going. So we're just going to take that approach here. And if we go into signing and capabilities, see disable library validation, see that adds that nice little entitlements file to our project. We try it again. And success, program ended with exit code 0. Cool. So we installed SDL, we got it set up on our Xcode project. Now what do we do? We figured out entitlements and we figured out how to run things past macOS security. Okay, so the first thing we want to do is create and display a window that we draw onto. So to do that, we call create window, set Pong as the title. So it asks for X and Y coordinates for where our window spawns, and we're just going to say undefined because we don't really care. As long as it shows up on the screen, it doesn't really matter where we start. And we're gonna set the width and height to just a sort of standard, let's say 640 by 480. We're writing an old school game, so let's use an old school resolution there. And we make width and height constants because that's just going to help us do some other calculations a little bit later on. And our final parameter is flags. Now, we could have just set that to 0, but by adding SDL window shown there, we just tell the OS, okay, as soon as you create the window, just go ahead and show it. If we did not have that SDL window shown there, then we'd have to do something like this. But yeah, that's pretty much all that's going on there. So okay, let's go ahead and run this and see what happens. So our program started, it initialized SDL, it created a window, and then it exited immediately. Okay, well, what do we have to do here? Well, in order for our window to stay up, and in order for it to kind of process events and figure out how to respond to different bits of input, we need to create what's called an event loop. Now, there are a couple of event loop functions in SDL, but the one that we're going to start off with is called SDL wait events. Wait event. So what SDL wait event does is it basically puts our program into an idle state and it waits for a signal from the OS to come in. So if we get a quit signal, let's say that we hit Alt F4 on Windows or Command Q on Mac, or if we get a keyboard event or a mouse event, then SDL wait event is going to wait for stuff like that to happen. And this event parameter that it takes is going to get filled in with the information about the event that we received, and it's going to allow us to kind of respond to that event inside of our application. So let's set up a basic event loop. All right, so this one's pretty simple. We're just saying wait for an event to happen. If we get an event and that event is of type quit, then just break out of our loop, and that's it. So let's see what happens. And there we go. And if we quit out, then our program ends. Perfect. And oh, hey, Hector showed up. How's it going, Hector? And Try is here. How's it going, Try? Good to see y'all in the stream. So yeah, UB stands for unsigned byte. For those who are unaware, it's one of my many aliases. Uh, yeah, so let's kind of keep things going here. And of course, if there are any questions, then just hop into that chat and throw them out there, and yeah, we'll go ahead and get those answered. Okay, so getting a blank window up and running is a great first step, but in and of itself, obviously, it's not very interesting. So in order to actually draw our game components on the screen, we're going to need something called a renderer. Now, SDL comes with a basic 2D renderer, one that can roughly be thought of like a Super Nintendo, but with higher resolution and higher color depth, obviously. So it can load images, draw, scale, rotate, do basic transparency, and it even gets hardware accelerated by your graphics card. So if you're on Mac or iOS, it uses Metal behind the scenes. If you're on Windows, it uses DirectX, and on everything else, it uses OpenGL. And if you don't know what those are, that's fine. They're just ways that your game talks to your graphics card. And the point here is that SDL tries to pick the most efficient option for your platform. So let's go ahead and create a renderer and set our clear color and just render a blue screen. Let's do that. All right, so create renderer, and we're creating it on our window that we just created. For index, the index actually refers to the index of the graphics card that you're using. And if you just want the default, you could put -1. And then under flags, there are a lot of options that we could put under flags. For right now, the only one we really want is accelerated. And that basically says use our graphics card to do the rendering instead of using our CPU to do the rendering. All right, so that's step one. Next, we're going to want to set the draw color. and we're going to set it to blue. So these RGBA values, they're unsigned 8-bit integers. They go from 0 to 255. So our red's going to be 0, our green's going to be 0, our blue is going to be 100%, and our alpha is also going to be 100%. And then we're going to say clear, and that's going to go ahead and clear our screen. So let's see what happens when we run this. Okay, nothing. Our screen's still black. What gives? So most computer graphics systems use a technique called double buffering. And what that basically is when we issue these draw commands, render clear, draw rectangle, what have you, all those commands get executed on a piece of memory that's not currently displayed on the screen. And what the system does is it renders stuff to that off-screen space of memory. It's usually called a back buffer. And when the operating system requests a new frame to display on our screen, it swaps that invisible back buffer out for the one that's currently on the screen and displays whatever it is you're drawing to. So this is actually a technique to kind of alleviate certain types of artifacts. Like if you ever use, say an old version of Windows, like Windows 95, Windows 98, you might have noticed like you drag stuff around, there's a lot of flickering and stuff. That's because the operating system didn't double buffer. You could double buffer inside of games, but that was something that you had to like kind of implement yourself. But yeah, in SDL, that's sort of an implicit thing here. So in order to actually get our fancy blue color to show up, we need to do another function call. And that is render present. And that takes what's on our off-screen buffer that we've been drawing to, and it signals like, hey, it's time to show this onto the screen. So let's see what happens here. Now we got blue, like we expected. Cool. So we know that our renderer works. We know that we can, at the very least, clear the color. Yeah, now let's do something. Now let's do some really basic rendering here. So our Pong game is going to be made out of rectangles, and we're gonna start by drawing the ball. So before we get into drawing, let's talk a little bit about coordinate systems. So I'm gonna open up Paintbrush here. That's good. Okay. So let's say this is our screen. No, here we go. This is our screen. And we have a width of pixels going this way. We have a height of pixels going this way. And with our coordinate system, our origin point is going to be this top left corner. And there's not this specific sort of scientific reason that the top left is sort of always the point of origin. It more or less has to do with a number of cultural conventions that sort of cascaded into just that's the way that we do things. It just so happens that the old cathode ray tube TVs, back from the 30s or whatever, would start at the top left and then go across to the right, and then they would scan back around, and then they would go over the next line and then scan back around, go over the next line. And that probably happened because TVs were invented in a country where people speak and read English, and English is a left-to-right language, and that's just sort of how this top left corner here ended up being our point of origin. But there are some systems that don't work that way. So, just something to kind of keep in mind there. So if we're talking about pixel coordinates, then at this top left corner, our x position is going to be 0, and our y position is also going to be 0. If we go over here, our x position is going to be our width, which we said is 640. And we're still up at the origin for the y coordinate. We go down here, and our x coordinate is going to be 0. Our y coordinate is going to be our height, which is 480. And here, our x and y are going to be the max values. So let's say we want to draw a rectangle right smack dab in the middle of the screen. Let's say this is the absolute middle. And let's say that rectangle is 10 by 10 pixels. And this is our midpoint. Vertically, straighten that out. And this is our midpoint. That's definitely not the midpoint. And this is our midpoint horizontally. Now this little, just pretend this is symmetrical. Now this little square in the middle, it has the same coordinate system as our screen does, where the origin point is going to be this top left corner. So if the square is 10 by 10 and we want it to be in the middle of our screen, then what we need to do is have our x coordinate be half of our width, so 320 is half of 640, minus half of the width of our sprite. And this is, we said this is 10, so this is going to be 5. And then our y coordinate, correspondingly, so half of 480 is going to be 240. Minus 5. So our x and y coordinates for this rectangle are going to be 315. And 235. And then, of course, the width and height are going to be 10 the way that we expect. So now that we have kind of this context, I can go ahead and write the code to actually draw that rectangle in the middle of the screen. So I'm going to change our clear color to black again. And we clear the screen. And then after we do that, we're going to set the draw color to white. So we want to specify our x coordinate, which is going to be the width of the screen divided by 2 minus, actually let's go up here, and we'll define a variable called ball size. It's going to be 10. So it'll be 10 width and 10, it'll be 10 wide and 10 high in pixels. Do ball size divided by 2. Okay, so that specifies our rectangle. We say full rect. pass the address to our fillRect function. Let's run this. And there we go. We've got a small white rectangle right in the middle of the screen. Okay. Okay, great. So most games involve updating the screen every frame and doing some sort of animation. Yeah, so in order to do this in our application, we need to kind of make a few adjustments. So for one thing, all our app is doing right now is firing up, and it paints the screen once, and then it just kind of idles and it waits for us to hit that exit button. In order for us to do animation, we're going to have to update the screen at a pretty consistent rate. My monitor, for example, updates at 60 hertz. Some fancier monitors update at 120 or even 240 hertz. So we basically need to call this rendering function for every time that our screen updates, and that's how we do that, and we make some changes to our coordinates, to our parameters here, and that's how we get animation. So for one thing, we're going to have to change this SDL wait event, and instead we're going to be using something called SDL poll event. Poll event is like wait event, except it doesn't wait. And the idea is, all right, so back up a little bit. So for one thing, actually, let me go up here. So we're going to need to use bool. And if you come from a C++ background, bool is actually a part of standard C, but it's implemented as a library for some reason, so you need to include studbool.h. Some weirdness, go figure. But it is what it is. So we're going to restructure our run loop to look like this. Okay. So if we end up running this, it's gonna look exactly the same as it did before. And it's gonna work mostly the same as it did before. The only sort of difference there, and you could actually click on this tab over here, and you can see like we're using a lot of CPU right now. And that's because this loop is basically, it's not blocking anymore. So wait event would suspend the thread until we got a message from the operating system. What poll event does is it checks to see if there's any messages in the queue. If there aren't, then it just returns immediately. If there are, then it fills out the SDL event struct, and we can respond to events, and that's pretty much how it goes. Yeah, so this is going to help us update every frame, but we probably need to do something about this 100%, 102% CPU usage there. I didn't know you could go 102%, but okay. So actually, let's go ahead and start off by taking this render code. Let's do a little bit of refactoring first, because our main function is getting a little bit unwieldy, and that is not a good thing. So to kind of break this out into steps, want an initialize function, you want an update function, and we want a shutdown function. Go ahead and implement those. So let's take our init code, pull it out from here, drop it into here. Instead of exiting, we're going to return false. And we're also going to add some error checking here. There we go. Okay, next we're going to do the update function, and the update function we're going to get to in a minute. The parameter for that we're going to call elapsed. And we will get into all of that very shortly. And then our shutdown. So yeah, we kind of broke things up here because we separated the declaration of our renderer. We put it inside of the scope of this initialize function. So for now, we're actually going to make these into global variables, and there's something to be said about that, but kind of bookmark that thought, and we'll come back to it. So we're going to make window and render global. Put it up here. So window and, yeah, so global variables in C, yeah, by default they get initialized to like whatever their zero value is. But just to be thorough, we can put null here, null there. A little bit of extra documentation never hurt anybody, so assuming it's accurate, right? So we take this away because we're going to be using our global. Take that away. All right. So now one thing that I kind of neglected to do before was properly shut things down. Like we had SDL quit, but we're gonna want to clean up the window and renderer as well. And for this little application, it doesn't really matter, but when you get into more complex applications, you know, resource management in C programs is, it's a much more explicit thing than it is in other languages, where you have automatic reference counting, or you have garbage collection, or you have something that you know, cleans up objects when you're not using them anymore. So just to be thorough here, we're going to put destroy renderer, destroy window, and quit. Now, instead of calling shutdown directly, what I like to do is at the start of the program say add exit shutdown. And what this does is if we specify this, then the function that's at this address is going to get called whenever our program exits. So that's just a nice way to kind of clean things up. And we call our initialize function. It's false. Then exit. And that'll automatically call our shutdown function. Now, back to the business of global variables, you probably noticed that we're doing a little something here that may or may not be safe to do. So let's say, get rid of some of those comments there. Let's say we call initialize and we fail right at SDL init. return false. Then we go here, we exit, and then we call shutdown. What's going to happen? It's going to call our shutdown function, and it's going to do SDL render, destroy render. Oh, but wait, render is null. Now, maybe a destroy render is resilient and does null checks internally. Maybe it doesn't. Maybe this is going to produce an error. Maybe it's going to segfault and crash our program. Doesn't matter a whole lot because we're already exiting, so whatever. But, let's say that we have some more sophisticated cleanup to do and our program crashes before we have the opportunity to do that. This is one example of the perils of global variables. So now I'm in the situation where I have to consider the global state of my program and every possible state that this could be in whenever I call it. And if it had a narrower scope, then that would narrow out the possibilities of how many potential states it could be in. So the fix to this is pretty simple. Just put a null check around it. And bam, problem solved. All right, so let's go ahead and go to our update function now. So all this stuff is going to be in our update function. And our update function is going to be called inside of this loop here. Not this loop here, but this loop here. So what pull event does is it basically goes through the entire event queue, it empties it out, and it allows us to check against whatever events are in the queue. Once that queue is empty, we drop back down here, and we have to update the state of our game. Now, you might have noticed we added this parameter, elapsed, and what we want to do is we want to provide our update function with how much time has elapsed since the last frame that we rendered. And the reason we do that is to keep animations consistent across different speeds of execution. So let's say my computer can run the game at 50 frames a second, your computer is a beast, it can run it at 100 frames per second. Regardless of how fast our computer is, we want it to be updating the game at a consistent speed. So that's what the elapsed allows us to do. So how do we get that? How do we derive that? So we need to keep track of the timing of the previous frame and compare that with the timing of the current frame. So we have this function in SDL that's called SDL get ticks. And SDL get ticks, that returns the number of milliseconds that have passed since we called SDL init. So your program fires up, and then it starts counting 1, 2, 3, 4, 5. It just counts up until it runs out of numbers to count to of the number of milliseconds that have passed. So we have that we keep track of. Let me say we get the time for the current frame. Yeah. Okay. So that allows us to calculate elapsed time. And there's another aspect of this that we're going to want to not forget, and that is to update the last tick to current tick. So we pass that elapsed into our call to update. And that basically allows us to say, like, okay, this fraction of seconds have passed since the last frame. So, animate at this level, or at this much of a step. So like if we want to set, say like the speed of our character to, like 100 pixels per second, we can just say 100 times elapsed, and that kind of does it for us. As to why we're converting it from milliseconds to seconds, seconds are just a little bit easier to reason about. Human beings kind of operate in the space of seconds. So yeah, that's kind of what that is. So this should run. And it does. And it does the same thing as before. Now we can actually save a little bit on battery life here. And we can also improve our image quality a bit. By going to our render setup and adding a flag to it, present vsync. So what this is going to do is it's going to sync up the updates to whatever your monitor's refresh rate is. So if your monitor is 60 hertz, then it's going to cap you at 60 FPS. And that's good because, it's more efficient. And not only that, but if we're synced up with the FPS, then that's going to prevent tearing as well, and that's a good thing. So we have this update loop going, we have this elapsed time going. So yeah, let's animate this ball. So I'm going to make things a little bit more structured at this point. Going to create a struct called ball. Okay, and that's going to kind of encapsulate basically all the information about our ball. So we have the x and y coordinates, we have the x speed, the y speed. So, x speed is how many pixels per second it's moving horizontally, and y speed is how many pixels per second it's moving vertically. And you'll notice that these are all floats, and that our update method is also a float. And that is because, for one thing, we're operating in the space of seconds, as I mentioned earlier, converting up from milliseconds. And also having these as floats gives us subpixel accuracy with our updates. So even though we're rendering things at the pixel level, we're still going to animate things at a subpixel level, and that's going to add a sort of smoothness to our animations. Now, if you come from C++ or C# or Swift or another language that has structs like this, you're probably wondering what all this extra ceremony is about, the whole type def struct and all that stuff. So C is a little bit weird. This would totally be valid. The sort of irksome thing about this, though, is that if I declared the struct this way, then whenever I called it, or whenever I referenced it, whenever I instantiated it, it'd have to be like that. And that's a little bit tedious, it's a little bit wordy. But what I can do is kind of add a type def for it. And, that allows me to kind of declare it the way that, I do like an integer or like any other type. So a shortcut to that is what we had before, which is bam. Right. So, okay, so we have this ball struct, and let's see how we can kind of integrate that into our whole animation system here. So let's create a function called makeBall that's gonna like kind of act as the constructor for this ball struct. Or declare it there. We could get rid of that. We can say, oh, we got some errors. We'll fix those later. Okay, so let's say that's going to be our speed, just 120 pixels per second, and either X or Y, like whatever direction we're going in. 120, negative 120. And we kind of fill out the fields here, turn there. So we're still starting in the middle of the screen, as you might remember from our rec definition. And for speed, we're going to do something a little bit different. So, okay, gonna write a little helper function here. And I need to seed our random function. So here, I'm just going to say we'll call it srand. And we all know how terrible rand is, but yeah, we're not talking about that today. And then we're going to say size. So it's going to set that to our parameter. Cool. Now we have fancy makeBall function. Let's make that a global, yet another global. And if you're new to C, there are ways of scoping out data. Particularly the static keyword allows you to kind of keep things within file modules. And And that's generally one of the big tools that you use in C for information hiding if it's something that you want to do. So, if you're new to C, don't think that it's just a free for all where, like you can access whatever you want to. There are ways of kind of structuring larger programs, which we'll get to later on in the series. So yeah. Yeah, so we're calling make ball inside of our initialize function. That just does our. I probably should have kept ball size. Yeah, that just does all that. That's just a way to name all of our setup stuff. Now we're going to want to update our update code here to render the ball based on the parameters of the of our ball structure. So we're going to create a new function, yet another function, and we're going to call it update ball. Actually, we're going to call this one render ball. Okay. So, and yeah, we gotta name it. So for the ball that we for the ball object that we provide, we just need to do all that SDL fill render fill rec stuff that we did before, but we're just kind of isolating where it is. So. And we set our draw color to white. And we go ahead and draw that rectangle we just defined. Okay, so that draws our ball. So we can go back up to our update function here, and we can actually get rid of. Yeah, we can get rid of all of this. We can say. Render ball, and at this point, everything should be the same. But now we've just added a bit more structure to things. Okay, it's actually in the wrong position. I expected it to be in the middle. It's sort of in the middle, but it's sort of down a little bit, so probably messed something up here. Oh, I did width and width, so width and height. And bam, we are right in the middle again. Oh, I forgot. Okay, so yeah, so the reason that I made this coin flip function, yeah, I sort of Uh, yeah, I lost my place there. I'm supposed to... Yeah, we're supposed to initialize the speed of the ball for the x and y directions. So let's say... So yeah, this basically says, either initialize our x and y speed to either 120 or negative 120. Cool. What's going on, Nan King? Nice to see you in the building today. Hope the day is treating you well. Hope the heat's been treating you well. Speaking of heat, gonna take a quick drink over here. All right. So let's go ahead and implement our update ball function. And let's use all that fancy timer stuff that we implemented. And furthermore, let's make sure that it actually works. So prototype. Whoops. No, it's not going to be const. All right, so we're going to make a function called update ball. Let's put that there. Okay, so we're going to start off by basically making it bounce around the corners of the screen. So we have pretty much all the information that we need to do that. What we want to do is, first and foremost, is update our x and y coordinates based on our speed on the x and y axes multiplied by the elapsed time since the last frame. Whoops. Okay, cool. Step one. If we run this now, then we should see it. No, it's not doing anything. It's not doing anything because we're not calling update ball. Okay. But if we call update ball, see here. And it sort of just goes off into infinity. So what we want it to do is bounce off the corners of the screen there. Now, in order to make that happen, inside of this update function, we're going to say so if ball.x is less than 0, that means we're going to be on the far left corner of the screen, and we're going to set x speed to the absolute value of x speed, which is going to be positive 120. And on the opposite side, if it's greater than the width minus the ball size, so like that way we don't have the ball go off screen, then we do negative of absolute value, and that just does exactly what we want. And then we do that for y coordinates. Hey Angie, how's it going? The venerable Angie is crossed into the stream. Always good to see you. Always an inspiration. Hopefully one day I'll be half as good at this as you, but just take my baby steps here. Hope your evening's going well. I almost did it again. Mixing up width and height there. Cool. Let's try and run this and see what happens. Ah, where did it go? There it went. There we go. We're bouncing around. Boop, boop. Boop, boop. Oh, that's right. Okay, so yeah, when I coded this up, I was kind of working off the assumption that the x and y coordinate for the ball would actually represent the middle, and that just felt like a bit easier to reason about. But yeah, you can sort of see the fallout from that, which is our ball is bouncing off the far corners a little bit prematurely, and it's bouncing off these the left and the top corners a little bit early. But if we go ahead and adjust that just a bit. And there we go, perfect. So we're gonna need some paddles for our Pong game, obviously. But hey, we've accomplished a lot so far. We got an animated screen up and running. It runs consistently, regardless of how many FPS we're getting. So yeah, we're in pretty good shape here. So let's start talking about our players. So to represent a player, we're going to need a few things. We're going to need let's go ahead and make another struct called player. We're going to need to keep track of score and y position. That's basically it. all the other stuff we can kind of have like kind of be implicit or semi-implicit. Like it's not something that's required for every instance of player. For example, player width, like it's always going to be 20. Player height, say 75. So I'm also adding this variable called player margin. And margin is just going to be the number of pixels away from the edge of the screen. And it's a little bit nicer than just having the paddle be like right up against the edge of the screen there. And I'm also going to have a move speed constant. Okay. So now we have a good deal of information about our player, how it's going to work. So there are going to be a few methods that kind of control the operation of the player, a few functions. We'll set up initialization. Update. It's also just a good pattern to kind of separate your updating from your rendering. And the reason you want to do that is to prevent the sort of odd cases where the state of the game is somehow derived from the state of rendering data. Like you want it to be a one-way sort of flow where you're getting player input and you're updating the state of your game and then you're rendering the state of your game. And you're not like kind of going back and forth between those stages. You're just always going in a straight line from get input, update state, render. When things get more complicated, that's just gonna simplify your ability to kind of reason about what your game is doing. So it's a good sort of practice to separate out updating from rendering. All right, let's go ahead and implement these. So make player is going to be pretty simple. And we're done. Like all that really does is just put the player Y position in the middle of the screen. That's pretty much all we need to do. One thing to note if you're sort of new to C, so like you might notice that we omitted score, and by default, when you do this sort of initialization in C, any fields that are not specified in your initialization get set to 0 automatically, or whatever the 0 value is for the type. If it's floated, 0.0. If it's an integer, then it's the number 0. If it's a pointer, then it's null. You get the picture. So now we want to update our players. So we're going to get into something a little new here. So SDL lets us read our keyboard state, and we're going to do it in sort of a not the best way, but it's going to work for this project. So we have this function called get keyboard state, and it returns. Probably find it here. There we go. And it does exactly what you think it does. You make a call to it, and it returns an array of bite-sized elements, and you can index in that array using these scan code constants. And that's how we're going to be able to read, so we're gonna go ahead and map the player on the left to W for going up and S for going down, and we're going to map the player on the right to up arrow key for going up and down arrow key for going down. So go ahead and do that. There's an optional argument there that allows us to read like the number of keys it returns, and it may or may not be useful to you. In this case, it's not really useful to us. So we're gonna do, well, first of all, let's add a starting state to our game. So if we go ahead and run it now, you're going to see that pretty much immediately our ball starts bouncing. But when we're playing, that's not going to be fun. Like as soon as you fire up the app, the ball's bouncing around. You want to be able to serve the ball. So let's create another global. Let's call it served. And so here, we're going to say if we press the spacebar, then set serve to true. And the way this array works is that if the key is not being pressed, then this index is going to return a 0 value, and if it is being pressed, then it's going to return a non-zero value. So that's how we use it in the if statement there. So let's go back to our let's go back to our update ball, and let's change this here and say like if not served. If we haven't served it, then just keep it in the middle, and we can go ahead and run this. And oh, I actually did the thing again. So I'm kind of typing in the dark here because the sun went down while I was doing the stream. Let me turn the light on. Lights, I can see. Awesome. Okay. All right, so our ball starts off not moving, and then I press the space bar. Okay. If you actually call your update functions, then they'll actually update. So yeah, my mistake here is that I didn't call update player. Is I'm not calling update players yet. So let me go into our main update method, and I guess I'll just call it here update players. That should do it. Or should it? Oh, I didn't define render players yet. Okay. It's fine, I'll just stub it out for now. Oh, hey. Cool. Okay, so when I press the spacebar, bam, ball is served. Let's actually turn our attention to this render players function for a second. So, yeah, so our left player is gonna be red, and our right player is gonna be blue, and just out of convention, we're gonna call the right player player one, the left player player two. That's generally how video games work. So so yeah, let's start off by just like declaring a couple of global player instances. Yeah, we can declare. I guess up here is fine, next to the ball. Player one, player two, and we're gonna have to call that make player function. Probably here is good. Cool. So what we want to do is we want to render something. So we got, let's go back to our good old friend Paintbrush. Okay, so we specified basically a Y position that represents the midpoint of our player paddle, and we have a few constants that we defined earlier. So we have player width, which is 20, and we have player height, which is 75. And then we have player Y, or Y position, which is right in the middle there. So how do we take the information from this player struct and use it to render a paddle that's sort of specified in this way? All right, so let's do that, and so let's set our draw color. There we go. To red. So as I mentioned, our player one is on the left side of the screen. So the far left is going to be 0 plus our margin. So for X, we're going to do player margin. For Y, we're going to do yeah, so that's that's basically taking our position and then subtracting half of the height from it, because our Y position represents the middle of the paddle, and then for width, height, Cool. Then cool. And then we basically repeat this for our second character. We're going to switch a few things around. To right, blue. So our x-coordinate here is going to be the width minus the player width minus the margin. So that's going to put us 10 pixels to the left of the very right edge. And this is pretty much going to stay the same, except we're going to change that to player 2. And these two are also going to stay the same. Let's go ahead and run this and see what it looks like. Okay. Both the paddles are showing up, but they're both red. And that's because I didn't update this this set render draw color. So red, green, blue. Blue. Try it again. And bam, there we go. And we can serve a ball. We can't move the pedals yet though. So that's going to be our next challenge. And I bet you can guess what our challenge after that challenge is going to be. Okay, so let's try and move these paddles. No, we're not doing that. Yeah, so in this case, we're going to be moving player 1. We're going to do player move speed times elapsed. And since we're going up, that's going to be negative in the y coordinate. Go down. All right, test this out. Up, down, up, down. Excellent. And now we do that for player 2. Try this out. Awesome. Okay. We're actually coming pretty close to the finish line. So the next thing that we need to do is implement collision detection for the players and the ball. So right now, ball just goes straight through the players. Not the funnest game ever. So let's go ahead and fix that. So SDL actually makes this super easy, in that we have all these rectangles, and SDL has a function called SDL underscore has intersection, and that's gonna return true if a couple of rectangles intersect each other. And we'll use that to change the trajectory of the ball when it collides into one of our players. So our update ball method is going to change a little bit. Actually, let's see here. Our update ball method is going to change, but maybe not now. Okay, our update players function is what's going to change. Okay, so after we process the movement, we're going to say actually, let's just go ahead and actually, we already defined this over here, so we can just copy and paste it. No big. Sometimes copying and pasting is not great. Other times it's whatever. For abstractions, we got the rule of 3, and right now we've only got 2, so we're good. All right, so let's say, so we defined our player rectangles and our ball rectangle. So let's say has intersection. There we go. And no. Cool. If you run this, awesome. Oh, we're going a little bit out of bounds here. Should be fairly easy to fix that. Okay. say let's do a lower bounds and an upper bounds on those positions. Let's see how this goes. Cool. Stops right at the edge. Copy that for player 2. Cool. Okay. So now we want to lose condition. What we want to have happen is when we hit either the left edge or the right edge, reset the ball and give the opposite player a point. So let's go back to we're going to do this in our update ball function. So instead of just bouncing off the edges, we're going to say, we're going to do something. Yeah, we're going to do something else a little first. So we're going to create a new function called update score. So SDL by default doesn't have any facilities for rendering text, and that's something that we'll get to in a later lesson. It actually involves importing a different library. But for now, we're just going to use the title bar of the window to display our score. It's cheap, it's hacky, but it works. So player 1 scored. Add points. Player 2 scored. Add points. So if you call snprintf with a format string, then it will return to you the number of characters that it would have outputted to a string if this was not null. So we're going to use that to initialize the buffer that the buffer that's going to hold our string that we're going to display. And this is a fun little C99 thing. If you're on an older compiler, this isn't going to work, but in I guess more recent updates of C, more recent being after 1989, you can actually use a dynamic variable to set the size of of an array that's that's allocated on the stack like that. Um, so we use, and snprintf is a bit safer. It prevents us from, it safeguards us from doing buffer overflows, which are a very common sort of exploit that happens in C programs. So if you can use snprintf or basically like basically any standard library function involving strings that has an in it that allows you to specify the length of something, that's generally going to be safer than the counterpart without one. So sprintf, a little bit dodgy, snprintf, pretty, a little bit less dodgy. And that's our score updater. Okay, let's go back to that line that we commented out. All right, so if the ball goes past the far left position, then player 2 is scoring. Let's call update score. Give player 2 100 points. And if it hits the opposite edge, then we give the points to player 1. Let's go back to update score. Let's say, just reset our ball while we're at it. Let's try this out. And let's have player 2 score. And we see our window title updated. Player 2's got 100 points and our ball reset. Awesome, awesome. And player 1 scored. And we did it. We made Pong. We made Pong in C using SDL. It's super cross-platform, super lightweight, and yeah, this is the start of something pretty cool. Maybe this is your first game. Maybe it's your first game in C. But yeah, either way, this is yeah, we're going to be able to do really cool stuff just from the sort of basics that we learned today. So yeah. So next time I'm gonna have a different game that we're gonna do, and it looks like this took us about 90 minutes or so. So yeah, I'm trying to keep these sessions about like between an hour and 2 hours. Looks like I've been going almost 2 hours here. So next time we're going to have a different game. It's going to be a slightly more complicated game. We're going to be going a little bit faster because, by now you should have gone through all this update stuff, or all this initialization stuff, rather. And so there are some challenges for you to kind of dive into until next time. One challenge is adding some AI to the second player. So if we run this again, yeah, so this blue player, it'd be cool if like when you served it, the blue player moved automatically, and then that way you could play this, against the computer. And AI for Pong should be It's about as simple as you can get for AI in a game. But yeah, you can try that out. One thing to sort of be mindful of is you don't want the computer controlled player to be invincible. So kind of think about ways that you would, like sort of fudge its actions and make its response to the position of the ball a little bit less than perfect. So that's one challenge. Another challenge, make it so that hitting the paddle at different locations has an effect on the speed of the balls. Like right now, the gameplay is pretty dull because like no matter how you hit the ball, it always just bounces off at the same speed. So to sort of add a little bit of spice to things, you could make it so that if we hit more toward the middle of the paddle, it sort of like goes faster horizontally. If it's toward the edge, it goes a little bit faster vertically, and that's sort of the fun thing about game physics is that you can sort of take a bit of artistic liberty and do things that are fun as opposed to things that are just say strictly physically accurate. Like if there was like no friction or no gravity in this like kind of abstract world that we created here, then I guess this would be physically accurate to some degree, but as it stands, it's not the funnest thing in the world. So yeah, kind of varying the ball speeds and kind of seeing what you could do to make that a bit more fun. Final homework challenge is our ball is not round. So SDL doesn't come with a routine explicitly for drawing ellipses and circles, but there are a few ways that we could do this. So you can go through the SDL docs and kind of figure it out yourself, or yeah, maybe we'll go through it on a future stream. So yeah, that's it. If you have any questions, feel free to hit me up in chat, via direct message in the comment section of this video. And yeah, if you found this helpful and you want to see more of it, then please like, share, and subscribe. And I guess that'll do it for now. All right. Thanks, y'all. We'll see you